Hello, welcome to week 5 of this NPTEL MOOCs course, Microwave Integrated Circuits. In the previous weeks or in week 4, we had covered the various microwave devices like the 1 port, 2 port, 3 port and 4 port devices. And while discussing 2 port devices, I had mentioned that these 2 port devices also include filters. But then since filters themselves are a huge topic in themselves, we will cover it separately. So in this lecture, we will be covering filters. Now filters, as you know, they are selective in which frequencies they allow to pass through them. And so based on this, we can have various types of filters like low pass filters, high pass filters, and band pass filters, and so on. Now, in microwave engineering, because of the distributed nature of the components, we can clearly classify the various filters that can be realized into 2 categories. One is what we call narrowband filters, and the other which we call broadband filters. So let us in this module we will be just discussing about the resonators and narrowband filters. So let us see what is a narrowband filter. And to discuss narrowband filters, it is very essential to know what these resonators are. Narrowband filters are nothing but resonators when properly input-output terminated. Now, what is this concept of resonance? Now, in EM field theory, resonance refers to the ability to store large and equal amounts of electrical and magnetic energy with minimal losses. Now, because the resonance as a phenomenon happens over a small band of frequencies, say this is our frequency scale, resonance happens over a small band of frequencies with a certain center frequency, say Fc or Fr. Then what happens is that the property of these resonators, that is the devices which create this resonance, is such that they have a center frequency and a certain range of frequencies about the center frequencies where the frequencies can be passed or stopped. So essentially resonators are like band pass components or band stop components. So what they, if I can elaborate what I mean, so you have a resonator will have a characteristics like this, a center frequency Fr with a range of frequencies where either the attenuation will be large or the attenuation will be less. Now depending on if the attenuation is large, then it acts like a band stop, and if the attenuation is large, then the resonator will act like band pass. Now you might ask, why are we directly going to band pass or band stop when from traditional filter theory we should have first discussed about low pass and high pass filters? The reason we go to this band pass concept or this narrow band concept, whether it is band stop or band pass, there is a narrow band of frequencies which will be either allowed or which will be either passed or attenuated, is because of the special properties of these microwave components. It is easier to realize a resonator than say lumped equivalents of or say equivalents of lumped components like L and C. So, because of the more difficulty associated with realizing equivalent versions of equivalent distributed versions of L and C, it is more convenient to actually build a resonator using microwave components. Now, this we have already discussed. For example, see a open stub. You saw that in the previous modules we had discussed that the same stub can act as an inductor or as a capacitor depending on the length or the frequency. If the length is constant and if you keep varying the frequency, then this open stub will act as an inductor for some frequencies or as a capacitor for some frequencies. So, we see that and in fact, it will act as zero impedance. That also we saw. There might be no impedance or the reactance itself might be zero for certain frequencies. Because of all these factors, it is actually, as we shall see, it is actually easier to design a resonator as compared to equivalents of lumped components in microwave engineering. Now, so that is the basic concept. That's why we have this concept of narrow band filters, because resonators are easier to build than L and C. Now, having said that, we do have a need for, say, broadband filters, where we have to design the response in the pass band and the stop band. So, for that cases, we do have some methods to realize the equivalence of lumped components. So, for example, if you want a design rather than a center frequency, you want a certain minimum attenuation in the stop band and certain maximum attenuation in the pass band. That is, your attenuation cannot exceed that value. So, in that case, you have to kind of, it is like a traditional filter design of the pass band, stop band attenuation, pass band attenuation. There we have to design the response, and there we have to rely on the traditional design philosophies, except that we also need to convert those lumped elements to their distributed equivalents, and that we shall see while we discuss this high pass, while we discuss the broadband filters. So, those topics will be covered in some modules, in some later modules, broadband filters. There the design philosophy is somewhat different from these narrow band filters. So, to summarize, for narrow band filters, resonators are the fundamental entity, whereas for broadband filters, we first design using the traditional filter design techniques using lumped elements, and then we have to find a mechanism to convert these lumped elements to their broadband, to their distributed equivalent. So then the next topic that we shall be discussing is about resonators. We all know what a resonator looks like. For example, a simple resonator circuit could be like this. This is what we call the series resonator. And a shunt resonator will be one where these R, L and C's are in shunt. Now, we can show that the total input impedance ZT of this resonator is given by RT plus J omega RL omega upon omega R minus omega R upon omega, where omega R equal to 1 upon square root of LC is called the resonant frequency. RT, suppose we also have a source resistance RG, then RT is equal to RG plus R. So this is the equivalent circuit diagram and the input impedance of a series resonator. Now here we define certain terms called quality factor. For a unloaded or for a series resonator like this, some quality factors, something called a QU, is defined as the unloaded quality factor, and its value is given like this. QE is the quality factor with respect to some external. For example, as I showed, if we have a generator VG with some RG connected, then this is the quality factor, and QL is the total quality factor, that is including the internal and external resistances. It can be shown that this relation is valid. Another way of writing the input impedance of a series resonator is like this, in terms of the quality factors that we just defined, where this epsilon f is equal to omega upon. Now the details about the derivation is given in the adjoint in the accompanying PPT files with this course. You can go through it. Now this epsilon f itself can be simplified to this value. Once again, the derivations, how we are doing it, is given in the accompanying PPT files. Now if we want to find out the total power dissipated in this system, that is both in the external and internal resistances, then so once again, if we draw our circuit, the total power dissipated is given by and this comes out to so ZT is this input impedance So this ZT can also be written as like this. Now there is a particular frequency or a particular value of this epsilon f, as epsilon f, as we saw, is a measure of the deviation of the frequency from the resonant frequency omega r. For a particular value of epsilon f, the power dissipated will be half that half the maximum power dissipated, and the maximum power is dissipated at resonance. Now one more thing I would like to understand, that for series resonance, at resonance the input impedance is low. For shunt impedance, we shall see that the input impedance is high at resonance. Yeah, another thing about series resonator is that whether for series or shunt resonator, is that the power dissipated, there is a certain frequency, where the power dissipated is half the maximum value, and the maximum value occurs at the resonant frequency. And that value happens when QL multiplied by epsilon f is equal to either +1 or -1. So then we will have two different omegas for which half power is dissipated. That is also obvious from this equation. That is, when QL epsilon f is either +1 or -1, the power dissipated will be half that when epsilon f is 0. And further, using the equation that I just derived, that is QL epsilon f is equal to +-1, we can obtain a relationship for 1 upon epsilon f is equal to FR into bandwidth, which we call the 3 dB bandwidth. Now, bandwidth is equal to F2 minus F1, which are the two frequencies corresponding to this condition. Now, this term is also known as fractional bandwidth. So, this is the absolute bandwidth. Bandwidth upon the resonant frequency is called the fractional bandwidth. So, in other words, 1 by epsilon f, which is equal to QF, is equal to 1 upon the delta. The delta represents the fractional bandwidth. Again, the details of these derivations are given in the PPT files. You can go through them. So, now one other definition which of the Q factor that is frequently used is in terms of the reactance, because in microwave circuits it's not always so simple to find out whether a circuit is inductive or capacitive. Now, in first case we have defined, say, QU as equal to omega L upon R. Here we are assuming that we have knowledge about L. But suppose we don't have knowledge. Once again, if we draw our series resonator circuit, then QU, that is without any loading, is given by this. The other way of defining this, another formula is like this. Now, using this formula, what happens is we don't need to know whether the circuit is inductive or capacitive. If we know the X and its dependence on omega, we can directly find out the QU. Similarly, say if we want to find out QE, then just this denominator R changes to RG. So, this will be equal to half omega R upon 2 dx upon d omega upon RG, omega equal to omega R, and QL will be equal to half of omega R upon RT. Now, proceeding similarly, we can also derive the same relations for shunt RLC resonators. I am not going through the derivation, but it can be found, as I said, in the accompanying PPT files. And we will see that for a shunt resonator, we talk in terms of the admittances, susceptance, and conductances instead of impedance, resistance, and reactance. And the relations for a shunt RLC resonator are very similar, as I said, but except that the admittances are used in place of impedance and so on. And you can go through it. Since they are the dual of these relations, I don't want to spend much time on them. Rather, I would now like to show some of the actual resonators, microwave resonators that are used. So let us see the characteristics of a shorted transmission line. For a shorted line resonator, the imaginary part or the reactance, if we plot the reactance versus the frequency, then we get a curve like this, which is a tan function, and this is periodic in frequency theta, f and L. If we plot the values of theta, or if we plot in terms of the length, now what we see is that for this shorted line resonator, there are some particular values or at certain frequencies omega 0 where the value becomes 0, and certain frequencies, say here, where the input impedance becomes infinite. So we saw that for a series resonator, our input impedance should be low. So say for frequencies 2n omega 0, this resonator, the shorted line resonator, acts as a series resonator, and say for omega equal to 2n plus 1 omega 0, the shorted line resonator acts as a shunt resonator. Okay, so the same shorted line can act both as a series resonator as well as a shunt resonator for different frequencies. Now coming, so this also gives a reason why, shows you a reason why I said that narrowband filters might actually be easier to implement than say broadband filters using lumped elements. The reason is that, as we saw, that the certain microwave components like this shorted stub or open stub are actually easier to implement, and hence, and because these have a band pass or band stop characteristics, so they are actually easier to implement, these particular narrow band filters, than say a broadband filter, which has to be first designed using a lumped element equivalent, and then those lumped elements have to be converted to their distributed equivalents. Now, can we improve the performance of this shorted or open stub? Can we do that? So one way to do that is what we call the gap coupled resonator. So gap coupled resonator has a construction like this, that this is our feed line, that is the main line which connects our resonator to the rest of the circuit. There is a gap, and say we have an open circuit resonator, and the equivalent circuit is like this. Now X in, that is the input reactance of this gap coupled resonator, is equal to Now, this beta r and corresponds to the frequency omega r, that is at the frequency where this structure consisting of the gap and the open circuit resonator acts like either a series or shunt resonator. Now, how do we find out that value of omega r? To do that, let us see the construction. Let us see the graphs or how the reactance of varies with frequency. This reactance that I just drew. Now, for an open circuit stub, the imaginary value of Zin or the reactance, input reactance versus omega curve looks something like this. This also, in terms of this omega 0, it can be written like this. And that capacitive reactance varies like this. So, the intersection of the two gives the frequency where it will resonate. In fact, the QE, suppose this resonator is connected to an external impedance Z0, then the QE value for this gap coupled resonator, it can be found to be like this. The advantage of this is that we can get very high Qs. The Q factor that can be obtained is very high using this gap coupled resonator. So, in summary, we saw how resonators can be easily built using some standard microwave component like shorted lines or open stub lines, and how we can improve the Q factor of these lines using a gap. In the next module, we will see how using these resonators we can actually build the narrowband filters. Thank you.